All right, let's wrap this problem up. So again, we were trying to take the Laplace inverse of this function f of s, right? We want to convert this to f of t, and we're doing that by assigning each one of these terms. We can use the linearity property to just state that this is basically a sum of three different functions of s. And we can say that the Laplace inverse of f of s is basically equal to the Laplace inverse of f1 of s plus the Laplace inverse of f2 of s plus the Laplace inverse of f3 of s. And then we can say that that's equal to f of t, which is equal to f1 of t plus f2 of t plus f3 of t, right? And in the previous video, we already found f1 of t and we found f2 of t, so let's grab those. F1 of t is here. I'm going to probably rewrite that f1. It looks horrible. So f1 of t is there. F2 of t is here. And we needed to find this f3 of t to complete this transformation. Let me rewrite this. That's way better. All right, so f3 of s here, right? We've got f3 of s is basically 8 divided by s squared plus 4s plus 5. Not immediately obvious that we can do something with this from the table, but we can if we do a little bit of algebraic manipulation. So hopefully you would agree that I could rewrite this as 8 over s squared plus 4s plus 4 plus 1, right? 4 plus 1 is 5. And now this is really easy to factor, right? I can easily factor that. I can say that this is 8 over s plus 2 squared plus 1. And now I could pull the 8 out, and I can say that f3 of s is equal to 8 times 1 over s plus 2 squared plus 1. And this right here is in the Laplace transform table. Let's go take a look. There is a term that we can match this up with in the Laplace transform table, so let's go look at it. This one in particular, this entry number 13 here, is saying if we have something in the numerator, an s plus a squared plus that same numerator squared, well, our numerator is 1, so this value for us is also 1, and we can use this. Let's take this with us. I think it's hopefully I can get a good screenshot here that's not too tainted by other stuff. Let's see. Yeah, that's good. Let's copy and let's go back to here. And I will put this right here. And so hopefully you can see how we can match these up. So this 1 is my omega. This 1 is also my omega squared. And then my a is 2. And so we can say that my Laplace inverse here, we'll call this f3 of t, is going to be e to the minus 2t multiplied by the sine of t times u of t, and then that whole thing's multiplied by 8. So let's just move that over and just say that it's 8 times e to the minus 2t, sine of t, u of t. Okay, so we've got our f1 of t, our f2 of t, and our f3 of t here. I'm going to copy this, put it over here. And so this final function of t, sorry, what did I do here? This final function of t, oh, how do I move this? There we go. I want to put a box around this. My final function of t here is basically just the sum of these three quantities up here. So I can say f of t is equal to, I guess I could just write u of t times 4e to the minus 2t plus 6t e to the minus 5t plus 8 e to the minus 2t sine of t. And that would be my final Laplace inverse transform, or inverse Laplace transform of my original function f of s, which I have here. Okay, and so this is, obviously this is confusing. You're just learning this for the first time, but this is much easier to take each term individually and just look it up in the table and take its inverse Laplace transform and then sum the results to get the final Laplace transform than if this were in some jumbled up form where we can't even use the table, and then you would have to go take this horrible integral, right, from sigma minus j infinity to sigma plus j infinity of something this hideous, right? So using the table is nice. This is our final answer. And what we're basically getting at here is that we can use something called partial fraction expansion to get our result into this form so that we can use the table and use this linearity property to our advantage, okay? So that was the point of this example, basically just to show how we can use the table. And partial fraction expansion is how we get there, and we haven't done that yet, so don't worry if these last two videos seem like they had nothing to do with partial fraction expansion. It's very related, but in the next video we're actually going to show how we can get the function of s into this form so that we can use partial fraction expansion. Okay, so I'll end this video right here, and we'll see you guys in the next video.